So we are headed into chapter 3, and this is quantities and chemical reactions. And we have a few goals for this chapter. We want to start thinking about when we go into the lab, do we just randomly mix certain amounts of chemicals? And the answer to that is no. We sit down and we calculate how much we want to mix or how much makes sense before we actually go into the lab. So that's the first goal of this chapter, is to figure out how to calculate how much of chemicals I mix together. The second one is how much product I expect to make. So I want you to think about, if you were the head of some company, why would the second question be particularly important? How much product I expect to make? And then we'll talk about, well, how do we figure out that difference between how much we actually make and expect to make? So before we do that, we need to talk about some terminology that we use in chemistry. It's going to be important when we want to calculate or answer both of those questions. So the first thing is the dozen for chemist. If we think about the comparison of looking at nails, we have a dozen nails, and they're different sizes and they weigh different amounts, right? We expect them to weigh different amounts. But we group them together in a dozen because it's hard to keep track of all those small nails. So if you go to the store and you want to buy a bunch of nails, you don't individually count them out. You usually group them together. So chemists do a similar thing, because if we're thinking about chemistry and those tiny little particles, whether they're atoms, molecules, or formula units, it's hard to keep track of all of those little particles, so we also group them together. And the way we do that is using the mole. So we can say a mole of anything. It doesn't matter what that something is. We abbreviate it as MOL, which never quite made sense to me. You're only getting rid of one letter. But 1 mole of anything is going to be 6.022 times 10 to the 23rd of whatever it is. It could be papers, it could be cars, it could be people. In our case, in chemistry, we're going to focus on tiny little particles. And again, we group them together because they're so small. When we're talking about those particles, we are talking about a lot of those particles, right? So if we look at a mole of different substances, so we have mercury oxide, sucrose, sulfur, and a few other substances. If we think about it, these are very different amounts just by looking at it, right? But for each of these, it represents 1 mole. So something else we can think about, just like the nails, 1 mole of different substances is going to weigh different amounts. The nice thing is we can get that information straight from the periodic table. Those masses that we see, that's going to be for 1 mole of that particular element. Okay, so here's one example. 1 mole of sulfur weighs 32.09 grams. And this also gives us another type of conversion factor. So I can always convert between moles and grams. On a side note, if your birthday is on October 23rd, like my husband's, that is a holiday. It's mole day. How big is a mole? So I recommend pausing the video and you can look at these on your own, but it is a huge number, 6.022 times 10 to the 23rd. So now we want to figure out what we can do with the mole, and I want you to continue to keep in the back of your mind that we're trying to answer those 2 questions. How much do I mix in the lab of reactants? How much product do I expect to make? So the first thing we can do with the mole is we can relate elements in a chemical formula. So this is the chemical formula of ibuprofen, and you have the structure here where the black or gray represents carbon, the white represents hydrogens, and the red represents oxygen. But what I can do is all of these subscripts are going to represent mole ratios. So what I can say is that mole of the whole thing, so C13, H18O2, I can relate it to the individual elements. So 1 mole of the whole thing is equal to 13 moles of carbon is equal to 18 moles of hydrogen is equal to 2 moles of oxygen. And again, notice that we now have conversion factors. So I can pick out any conversion factor that I want. that I need for a particular problem. I could say 18 moles of hydrogen is equal to 2 moles of oxygen. I could say 18 moles of hydrogen is equal to 1 mole of ibuprofen, the whole thing. Whatever conversion factor I need, I can use any of those relationships. So the second thing we can do with the mole is we can relate substances in a chemical equation. So that's where we're going with figuring out those two questions. Okay. The one difference for this will be, instead of using a chemical formula, since we're talking about a reaction, we're using an equation. And now all of the coefficients out front, after we balance the equation, those are going to be mole ratios. So what I can say here is 1 mole of ethanol is equal to 3 moles of oxygen gas. And what I'm producing, so I can mix those two together, and I produce 3 moles of water and 2 moles of carbon dioxide. Right? So we're going to focus on the top in a chemical formula first, and then we'll come back to the whole mole ratios in the chemical equation and see how this is going to answer our two questions. How much do I mix and how much product I produce? Which conversion factor to use? So when I'm thinking about this, I'm thinking about what goes into my get there. And I want you to look for a few words. So the first thing is, if I see units of mass in either my have or my want, then I automatically need a molar mass for whatever that substance is. Okay, so if I see any units of mass, it doesn't have to be grams, it could be ounces, it could be milligrams, it could be kilograms, but if it's units of mass, I need a molar mass in my get there. So this is figuring out what conversion factors we need. Second set of words to look for, if I see any type of tiny little particle, atoms, molecules, formula units, if I see any one of those words, it tells me that I need Avogadro's number. So that's 6.022 times 10 to the 23rd, that is Avogadro's number. And the last thing, I need to look at my have and my want and figure out, do I start and end with two different substances? So do I start with carbon dioxide in my have, but my question is asking for just carbon? That means I started with one thing, I end with something else. That tells me I need a mole ratio. If I'm talking about a chemical formula, that will be subscripts. If I'm talking about a chemical reaction, it will be the coefficients in a balanced equation. All right, so I urge you to commit these to memory because it lets you know what you need in your get there, how to start your problem. So here's what we can do with the mole. And notice that mole is in the center of everything. So I can convert between moles and grams using the molar mass. If I'm going from grams to moles, I'm going to divide by the molar mass. This you don't have to memorize. We can just figure out what goes on top, what goes on bottom to make things cross cancel. If I'm going from moles to grams, I'm going to multiply by the molar mass. If I'm going between moles and tiny little particles, same thing. I have Avogadro's number to help me do that. Notice I can't go directly from grams all the way to particles or particles all the way to grams. I always have to go through the mole. So here's an example of a problem. The average person exhales 36.84 milligrams of CO2, carbon dioxide, per breath. How many CO2 molecules is this? So the first thing I want to do is organize my problem. Okay. Again, you don't necessarily have to organize it the way I do, but if you take that extra step to organize your problem, you'll always get the benefit of the doubt. So what I have is this 36.84 milligrams of CO2. And what I want is CO2 molecules. So that's my question. And now I'm going to ask myself what I'm looking for, what those three things are. So the first thing, do I see units of mass anywhere? And in this case I do. I have units of mass right here in my have, so that tells me I need a molar mass of that substance, so that's CO2. If If I go to my best friend, the periodic table, and add those up, 1 mole of CO2 is going to be 44.01 grams of CO2. Okay, I've answered my first question. Notice one thing here is that I have grams of CO2 and I have milligrams here of CO2. So I probably need another conversion factor to convert between those. We know that there are 10 to 3 or 1,000 milligrams of CO2 in every gram of CO2. And let's put a 1 there, every 1 gram. My next question, do I see tiny little particles? So do I see the words atoms, molecules, or formula units in my have or my want? And I do. I have molecules here. So that tells me I need Avogadro's number. 1 mole of CO2 is going to be 6.022 times 10 to the 23rd CO2 molecules. All right. My last question is, do I need a mole ratio? Am I starting with one substance and ending with something else? Let's look at it. I'm starting with carbon dioxide. I am ending with carbon dioxide, which tells me I do not need a mole ratio here. Let's do a roadmap and figure out what we're converting. So I am starting always with my have. I have milligrams of CO2. And then I'm looking at my get there to see where I'm allowed to go next. What can I relate milligrams of CO2 to? And I can relate it to grams of CO2. The next thing I can do is I can relate the grams of CO2 to moles of CO2. And the last thing I can do here is relate the moles of CO2 to CO2 molecules. Right? So the last step is just setting up the problem. Again, you can do it stepwise. I like to do it all in one step. Just make sure if you break it up into smaller steps that you're not rounding until the very end. So we have 36.84 milligrams of CO2. We want the milligrams on the bottom to make things cross cancel. So 1,000 milligrams of CO2 for every 1 gram of CO2. Okay, so currently we're in, if we make things cross cancel, we are in grams of CO2. We want those grams on the bottom, so 44.01 grams of CO2 in every 1 mole of CO2. We get rid of grams on top and the bottom. We're currently in moles of CO2. We're going to follow our roadmap. Now that we're in moles of CO2, we can go to CO2 molecules. For every 1 mole of CO2, we have 6.022 times 10 to the 23rd CO2 molecules. Okay, we want to make sure we don't confuse moles and molecules. They are different. So if we go ahead and plug it into our calculator and keep in mind that we start with 4 significant figures, we should end with 4 significant figures, we should get this number. So 5.041 times 10 to the 20 molecules. And if we think about it, we should get a really big number because we're talking about tiny little particles. So that makes sense that we get a really big number. Let's try another problem. So for this problem, it says how many hydrogen atoms are in 2 400 milligram tablets of ibuprofen. So let's do our have, want, and how we are going to get there. So to start, we are given that we have 2 and we have 400 milligram ibuprofen tablets. So let's write C13H18O2. Okay, and since we're just multiplying that by 2, we have 2 400 milligram tablets. It's okay to just say that we have 800 milligrams total that we're starting with. What we want are hydrogen atoms. Okay, to get there, again, we're going to go through our same questions. So to start, do we have mass next to anything, units of mass? And we do. We have units of mass next to ibuprofen. So that tells me I'm going to need a molar mass. So go to the periodic table. Something to keep in mind is that your final answer may be slightly different than mine, depending on what periodic table you're using with the rounding. So as long as it is relatively close, then you are fine. For 1 mole of the ibuprofen, so C13, H18O2, the mass of that, I'm going to write it here just because of room, we get 206.31 grams of C13, H18O2. And I know it gets annoying having to write down the formula next to whatever value it is over and over, but we don't want to mix them up, so make sure you have whatever substance it is next to it. Our next question, do I see tiny little particles in my have or my want? I do. I have atoms here, so that tells me I need Avogadro's number. We know that 1 mole of hydrogen has 6.022 times 10 to the 23rd H atoms. Okay, so we are good there. Let's ask our next question. Am I starting with one substance and ending with something else? I'm starting with ibuprofen and I'm ending with hydrogen. So now I do need a mole ratio that relates this whole thing, ibuprofen, to hydrogen. So what I can do is say 1 mole of the whole thing is equal to, remember I'm looking at my subscripts to know those mole ratios, 18 moles of hydrogen. And we have the same thing we did last time. We're in milligrams, right? So we know that 10 to the 3 milligrams, or 1,000, will be in every 1 gram. Let's erase this and actually make it a conversion factor. Okay, so let's do a roadmap. And we are starting with 800 milligrams, and I'm just going to say IB for ibuprofen, so we don't have to write the formula. Right? From there, if I look at my get there, I can go to grams of ibuprofen. From there, I can go to moles using the molar mass, so I can go to moles of ibuprofen. From there, I can go to moles of hydrogen. So something to keep in mind is that I can't go to tiny little particles of that particular atom or element until I am in moles of that element. So now I can go to H atoms. Okay, so even though it seems like a long process, I'm still asking myself those same 3 questions, and then I'm looking at my get there to see where I can go next. So break it into smaller, more manageable pieces. Let's make sure we put a decimal there because it does matter. Okay, we're starting with 800 milligrams, and I'm just going to put IB again. Remember that ibuprofen is going to be this formula. And we have 1,000 milligrams of ibuprofen. Remember, we have milligrams on top. We want milligrams on the bottom to make it cross cancel. And for every 1 gram of ibuprofen. If I make things cross cancel, I'm currently in grams of ibuprofen. Follow my roadmap, I can now go to moles. For every 1 mole of ibuprofen, I weigh 206.31 grams. Get rid of those. I am currently in moles of ibuprofen, and according to my map, I need to go to moles of hydrogen. So for every 1 mole of ibuprofen, I have 18 moles of hydrogen, right? And then for every 1 mole of hydrogen, I have 6.022 times 10 to the 23rd H atoms. Okay, so I'm plugging that into my calculator, and when I do, I should get this with 3 significant figures. And again, since I'm tiny little particles, it makes sense that it is a big number. Next example. So how many nitrogen atoms are in 1.2 grams of caffeine? So same thing, let's set up our have, our want, and then how I'm going to get there. I start with 1.2 grams of C8H10N4O2. Okay, and what I'm being asked are how many nitrogen atoms. So we want N atoms. Okay, let's figure out what goes in our get there, and then I think from now you can go ahead and set up the problem. Okay, so let's go through our three things we're looking for. We have, do we have mass next to anything? And we do. We have units of mass next to the caffeine. So we know we need to figure out for every 1 mole of caffeine, how much it weighs. So if we go ahead and go to our periodic table, it's going to weigh 194.22 grams. And again, we want to make sure we label everything, even though it feels like we're writing it over and over. Do we see tiny little particles next to everything? And we do. We see nitrogen atoms. So that tells me I need, for every 1 mole of nitrogen, we have 6.022 times 10 to the 23rd nitrogen atoms. Am I starting with one substance and ending with something else? I'm starting with caffeine, I'm ending with nitrogen, so that tells me I need a mole ratio. For every 1 mole of the whole thing, of the caffeine, if I look at my chemical formula, I have 4 moles of nitrogen. Okay, and remember, anytime I'm missing something, if I go to my road map and I'm missing something, I can always go back. So we're starting with grams of the caffeine, C8H10, and from there I can go to moles using the molar mass, so I can go to moles of caffeine. And then from moles of caffeine, we said we can go to moles of nitrogen using the subscripts in the chemical formula. So moles of just nitrogen. And then from there, I can relate moles of nitrogen to nitrogen atoms. Okay, so go ahead and pause the video, set up this problem, and once you plug everything in, you should get this as your answer with 2 significant figures. So this is my daughter, let's say 7 months ago. Goes by fast. This was when she was 6 months. I thought maybe you needed a mental break. This is Brooklyn. So our next topic is empirical and molecular formulas. Okay, so we have 2 different types of chemical formulas. An empirical formula is going to be the simplest formula for a substance, and it's going to be the lowest whole number ratio for the different elements. A molecular formula is going to be the actual number of atoms of each element in a molecule of a compound. So I think the best way to look at these 2 is to look at an example, right? Usually when you go into the research lab and you make something, especially if you don't quite know what you made, you perform something called elemental analysis. And from that information, so I'll post the video on elemental analysis, and from that information you get back the percentage of the different elements. And from those percentages, you can calculate a chemical formula for it. So let's see how we set up this type of problem. Right? So elemental analysis of lactic acid, and we're given a molar mass here, shows these percentages of the different elements. So 40.0% by mass carbon, 6.71% by mass hydrogen, and 53.3% by mass oxygen. So the first thing we want to do is With any of these problems, if we're given percentages, we want to just make our sample out of 100 grams. So all of those percentages get converted to grams. Okay, so instead of having 40.0%, I have 40.0 grams of carbon, and I have 6.71 grams of hydrogen, and I have 53.3 grams of oxygen. And what we want is both an empirical and molecular formula. So let's just put formula here. Okay. The first thing we want to think always is I need to go from grams to moles for each one. And this is the most common mistake that people make. You have to go from grams to moles. So we need the molar mass for each of those. We know that 1 mole of carbon is 12.01 grams of carbon. 1 mole of hydrogen is 1.01 grams of hydrogen. And then 1 mole of oxygen is 16.00 grams of oxygen. Right? So the first thing we want to do is take those grams and go to moles. So let's do that for each of them. So let's set it up. And we want moles on top. So moles of carbon, 12.01 grams of carbon. We have 6.71 grams of hydrogen. For every 1 mole of hydrogen, we have 1.01 grams of hydrogen. And then for oxygen, we're going to do the same thing. Figure out how many moles we have. So again, we have to go to moles. If you just plug in the grams, you'll get the wrong answer. Okay, so let's go through, plug those into your calculator. You can keep the same number of significant figures as you start with. We'll get 3.33 moles of carbon. We get 6.64 moles of hydrogen, and we get 3.33 moles of oxygen. Once we are in moles, now those moles become subscripts. So we get carbon, and whatever we get here for moles, we're going to put that as a subscript, 3.33. For hydrogen, we have 6.64, and then for oxygen, we have 3.33. So we have that, and we know for a chemical formula we can't have decimals. So what we'll do is we'll divide by whatever number is the smallest. So divide by 3.33 for every single one of them. So we have to divide by the same number. And when we do that, we just get CH2O. So this is our empirical formula. Okay. Now, if we were to go through and divide and we didn't get whole numbers, then we would need to multiply every single subscript by some factor to get the smallest whole number ratio. Okay, so that would be another step. One question I get often is about rounding. If you divide and you get 0.96 or higher, you can go ahead and round that to a whole number. Right? So this is our empirical formula, and now we want to find the molecular formula. In order to do that, we need to find a molar mass for this. So the molar mass for the empirical formula, if we calculate that, is 30.03 grams per mole. Okay. The next step is we want to take the mass for the molecular formula that we're given in the problem, and we want to divide that by the empirical formula mass. So I'm going to put a little line here, and we're going to take 90.08 grams per mole, and we want to divide that by the empirical formula mass that we just determined, so 30.03 grams per mole. And when we do that, we get 3. Okay, so it tells me that I need to take my empirical formula and multiply every single subscript by 3. So I'm just going to say we have H2O multiplied by 3, but that's for every single subscript. And this will give us our molecular formula. So we get C3H6O3, and this will be our molecular formula. So I want to show you one other type of problem. So we have those there. And here's another type of elemental analysis problem that we'll talk about more in class. But essentially here we are taking a 1 gram sample of vitamin C, and we don't know the molecular formula, but we do have the mass of it, the molar mass. We place it in a combustion chamber. So anytime we're doing a combustion and vitamin C is an organic compound, we mix it with oxygen gas and we produce carbon dioxide and water. So it's burned and we have this chamber. So in this chamber we get the amount of water that's absorbed in grams, and we also get the amount of carbon dioxide that's absorbed in grams. So we can weigh the absorber before and after, and if we subtract these two, we can get the mass of carbon dioxide that we produced. We can get the mass of water that we produced. Now, if we think about this, our vitamin C formula, I'm telling you, only has carbon, hydrogen, and oxygen in the formula. So what we can do is we can figure out our grams of carbon dioxide, and all of our carbon gets converted to carbon dioxide. So from the grams of carbon dioxide, we can figure out the grams of carbon we originally started with. We can do the same thing for hydrogen. We can figure out the amount of water. All of our hydrogen has to go to water, so we can figure out from the grams of water how many grams of hydrogen we started with initially. Since we have a 1 gram sample and we only have carbon, hydrogen, and oxygen, if I know the amounts of carbon and hydrogen, I can subtract those from the mass of the sample to get the grams of oxygen, right? From there, our problem turns into a problem just like the one on the previous slide. So if I know the mass of carbon, hydrogen, and oxygen, I need to go to moles, and then the process is exactly the same. So I want you to try to work through this problem and get as far as you can, and then we'll talk about it in class. So here's some space for you, and there's the final answer for the molecular formula. Right? The last thing, something to keep in mind is that even when you get a molecular formula, many different compounds can have that formula, right? So they can be shaped differently, but have the same number of carbons and hydrogens. And what we call these types of compounds, they are called constitutional isomers. Okay? Also called structural isomers. They have the same chemical formula, but the way those atoms are connected are different, right? And because they have different connectivity of atoms, they have very different chemical and physical properties. So here are some examples where we have constitutional isomers, but notice that their densities are a little bit different, their boiling points are different, and this comes into play with how those molecules interact with one another, also known as intermolecular forces that we'll talk about later. But I wanted to point this out because even when you get a molecular formula from elemental analysis, you still need some other analyses to come up with an actual structure. So something to keep in mind that we'll talk about more in lecture.